Just as we saw integrating in polar coordinates in 2D, let's look at integrating triple integrals now in polar coordinates. Just as we saw in chapter 11, we've got two different versions. We've got cylindrical coordinates and we've got spherical coordinates. So the first question we want to cover up is, when do you use cylindrical versus spherical versus neither? The first question you want to ask is the region circular in some way? So just like regions in 2D, if the region is circular, then use polar of some kind, either polar coordinates in 2D or cylindrical or spherical in 3D. Next question you want to ask is the region a sphere? Now this could mean either a sphere, a full sphere, a hemisphere, a quarter of a sphere, a spherical shell, anything that looks like a sphere or part of a sphere. If that's the case, then you want to use spherical coordinates. If it's not spherical, if it's circular in maybe two of the dimensions, but not an actual sphere, then don't use spherical coordinates. It's just going to make it a mess. So instead, you use cylindrical. Now these are just rough guidelines, but this should get you through the vast bulk of the problems you're dealing with in polar coordinates. Let's maybe look at some examples. So first up, let's say we wanted to find the volume of the region bounded by these two surfaces, z equals x squared plus y squared, and z equals 9 minus x squared minus y squared. So we've got these two surfaces here. I see that this first one, z equals x squared plus y squared, the fact that it has an x squared plus y squared in here tells me that this surface looks spherical. And if we were to make a sketch of this, this actually looks like a paraboloid. And the second one also, it's a function of x squared plus y squared, so it's also circular. So, but neither of these is a sphere. Right? This is actually a parabola in z and x, or a parabola in z and y, and the same goes with the second surface. So this is not a sphere. So we will not use spherical coordinates. Instead we'll use cylindrical. So let's look at how we'd set that up. The volume here is going to be the triple integral over the region dv. And just like when we integrated in polar coordinates, this dv, well, we're going to have our limits of integration. The function we're integrating is just 1. We're finding the volume here. Now anytime that you go into cylindrical coordinates, just like when you use polar, we have an integrating factor of r. And then we have dz, dr, and d theta. Let's look at the limits of integration in each of these. First off, the outer one is the easiest. We've got this region here. If you were to look at a cross section of this from above, the x and y values, this is tracing out a full circle. So we're getting the full range of theta values. Theta is going from 0 to 2 pi. The r on here is a little bit trickier. We want to see where these two surfaces intersect. If we look at a cross section of this, so if we look at this in the r, z, if we look at r versus z here, the first equation says z equals r squared. So that looks like a parabola. Z equals r squared. Looks like this. The second one we can see looks like z equals 9 minus r squared. So it's a parabola that's just upside down. And we want to look at this region inside here. So we want to know, what is this value? What is this r value here where those two curves cross? That'll give us the furthest r value that we're looking for. So if we set the two equal to each other, if we set the two heights equal, we get r squared equals 9 minus r squared. So 2r squared is 9. So r squared is 9 over 2. So we take the square root of this, and we see that the furthest out r value we get is 3 over radical 2. So now, based on our picture here, that we see that the r values, there's no gap in the middle here, so our r values go from 0 all the way out to that outer r. So from 0 to 3 over radical 2. And then finally, the the z's range from the bottom curve to the top curve. So in this picture, the bottom curve is z equals r squared. The upper curve is z equals 9 minus r squared. Okay, now we don't have constant limits of integration here, so we can't use the box theorem on this. So we have to actually do this out longhand. Integral from 0 to 2 pi, integral from 0 to 3 over radical 2. Now this inside function we integrate with respect to z. R is constant, so we just pick a z up. And we evaluate from z equals r squared to z equals 9 minus r squared. dr dz, there's dr d theta. Now here we're going to evaluate. So we keep our outer integrals the same, 0 to 2 pi, 0 to 3 over radical 2. We plug this our z values in, and we're going to get 9r minus r cubed, subtract r cubed, dr d theta. Now at this stage, this double integral, the inside function is a function of r times a function of theta. Our limits are constant, so we can use the box theorem. Break this apart as integral from 0 to 2 pi d theta times integral from 0 to 3 over radical 2, 9r minus 2r cubed dr. This first integral gives us 2 pi. The second one, we do the power rule on each piece, and we're going to get 9r squared over 2 minus 2r to the fourth over 4 evaluated at those limits. So we can plug those in a calculator, and that'll give us our volume. So because the region was circular, the overview of this is that the z equals r squared, both of the upper surface and lower surface we could write in polar fairly easily, but neither of them give us a sphere. So in this case we use cylindrical coordinates, not spherical. Let's look at an example where we use spherical. Let's say now we're looking for, again we'll look at a volume of the region bounded by z equals square root of 9 minus x squared minus y squared, and z equals 0. So really this is just the upper hemisphere. So we go to set our volume up, and this will be the triple integral over our region, dv. Now when we go to spherical coordinates, the integrating factor we have here is a little bit more complicated. We'll see why this is in the next section. But the integrating factor, this will give us the triple integral over this r. The original r was in x, y, and z. That gave us that sphere. This is in rho, phi, and theta. The integrating factor we have here is rho squared sine phi, d rho, d phi, d theta. So this is one of those things, just like the r that crops up, this is one of these things that you'll, for the moment, have to accept or memorize, but once we get into the next section on Jacobians, you'll see why this is true. So let's go and set up our limits of integration here. If we look at this right here is just the upper hemisphere of radius 3, centered at the origin. So that makes our spherical coordinates the natural choice on this. If we write down our limits of integration, the rho ranges from the center of the sphere out to the actual radius. So this is the integral from 0 to 3 d rho. The theta, well, this is actually a full circle. If we were to look at this overhead, if we were to look at this in the xy plane, so from above looking at this, we get the shadow of this sphere is the disk of radius 3. So we've got the rho values goes from 0 to 3. The thetas trace out a full circle, so the theta goes from 0 to 2 pi. And the the phi, now again if we were to look at this sort of from the side, so this is the z-axis, this is the xy plane, we have just the upper hemisphere. So the thetas here range from theta equals 0 all the way out to theta equals pi over 2. And then we've got our integrating factor, rho squared sine phi d phi. Now, luckily, as often happens in spherical coordinates, we can use the box theorem on this because our limits of integration are constant and the function factors up nicely. So we can rewrite this as the integral from 0 to 3 of rho squared d rho, integral from 0 to 2 pi of d theta, integral from 0 to pi over 2 of sine of phi d phi. Now we can integrate each of these on their own. The first one gives us rho cubed over 3 from 0 to 3. The second one just gives us 2 pi. And the last one, the integral of sine, is negative cosine from 0 to pi over 2. And plugging in our limits, this first one we've got 27 over 3, which is 9, times 2 pi. And the last one, cosine of pi over 2 is 0. And cosine of 0 is 1. So this gives us 18 pi for our volume. So that's the gist on integrating in polar coordinates in 3D. So just to summarize those two main points on there, in cylindrical, you're going to take this triple integral. You're just going to change your limits of integration around so they're in terms of z, r, and theta. And you're going to have this integrating factor of r. Okay, and now when we look at spherical coordinates, we're going to take our triple integral. We're going to rewrite its limits in terms of rho, theta, and phi. And our integrating factor here is rho squared sine phi. And this will give us our transformation into polar coordinates for triple integrals.